Okay, let's get started on this problem here. This is a problem with three blocks. They're all connected by cords here, and we're assuming the cords are massless and inelastic. And there are two pulleys in our scenario here. They are also we can consider them to be massless as well and frictionless. So we're just looking at a nice simplified version of this problem, and we're told something kind of important in the problem statement here. It's all important, but this really stands out. Assume block C descends with constant velocity. So that's a really special case, right? Where we have block C. So everything's in motion. It is descending. It's descending with constant velocity. So that tells us that our acceleration is zero. Pretty cool. We're given phi, the angle of inclination of the ramp. We're given the masses of blocks A and B. We are not given the mass of block C, and we are given the coefficient of kinetic friction between the surfaces at both interfaces. And when I say both interfaces, what I'm talking about is this interface between block B and the incline, and between block A and the surface beneath it. So there, we're using the same coefficient of kinetic friction, m sub k. All right, cool. And this is just, it's all in motion here, so we don't have any static friction. So let's go ahead and start this one. Now we have three bodies here, but we can handle that. What that means to us is that we're going to have three free body diagrams. So I wouldn't um, try to get too wrapped up in this until I got my free body diagrams down and then proceeded the way we always do here. So my free body diagram, and I'm going to lay these out where I have a little bit of space down here. My free body diagram for block A, block B, and block C. And I'll lay out my pertinent equations above here. Of course, Newton's second law. And then what else do we care about? Coefficient of kinetic friction is the product of the force of kinetic friction is equal to the product of the coefficient of kinetic friction multiplied by the normal force at that same interface. And yeah, I think that should do it as far as that goes. So let's launch into our free body diagrams. That is where most of our physics takes place, is when we draw these. Super important. I would never want to see a student trying to solve a force analysis problem without a free body diagram. Okay. So I mean, you can start with any of these. If you want to start with the simplest one, just go to block C, right? And that's going to be the simplest free body diagram. So if you want, we can start there. As always, my bias would be positive in the direction of acceleration. And, in this case, we're told that block C is descending with constant velocity. Later on in the problem, we're actually going to be asked to find different things to find the acceleration of C if we cut the chord between A and B. And so that sort of looking ahead, I know that I would want positive to be in the direction of motion, which is going to end up being in the direction of acceleration. So for that reason, I'm going to say positive downward because that will be the direction of velocity for the first part of the problem, and it'll be the direction of acceleration once we get to part C. So downward positive, and then the forces on C, I get my one invisible force, which is the weight of block C. And then the only thing that's touching block C is the cord it's attached to. So that's the tension there. All right. Now that's it. There's nothing else touching that block. So that free body diagram's done. I'll go now to maybe go to block A next. Maybe that's the next simplest one. It's on a horizontal surface. So I have my one invisible force, which is the weight of block A directed downward. And then I look at what's touching the block. Well, it does have the cord attached to it. In this case, the cord is providing a tension that's to the right. So right now I want to pause for a moment because I have two T's on my page and they are not the same tension. They're not connected to the same cord. I can't make assumptions about those two tensions. So I need to call them something. So you could label them as subscripts, whatever, for this this particular label, I'm going to use prime. So I'll call this the tension between blocks A and B. I'll call that T prime. And then the tension between blocks for the chord between blocks B and C, I'll call that T double prime. And remember that pulleys do not change the tension for us because we are assuming our pulleys are massless and frictionless. We don't yet have the analytical tools to deal with pulleys with mass. Once we do, toward the end of the quarter, we will see that for an accelerating system, the tension is not the same on either side of the pulley, but we'll get there. That's a complexity that gets added in later. Right now, our pulley is massless. So good news, the tension is the same on either side of the pulley for now. Okay, so that's notation for tension. Go back to block A. What else is touching it? Apart from the cord, it's only in contact with the surface beneath it. Surfaces, remember, can exert two types of forces. They can exert normal forces, normal to the surface, I'll call that N sub A, and they can exert frictional forces. So this is going to be coefficient of kinetic friction. I'm going to call this F sub A just to kind of keep it straight. These are all kinetic frictions, all the ones that I'll have in my paper. But I know that I'm just talking about the kinetic friction on block A. Nothing else in contact with block A. Now I can move on to B. So block B is on the incline. What we'll do here then, remember, is we will rotate our coordinate system only for block B. So you can kind of imagine a rotated coordinate system for block B only. Oh, and I'm going to put my sign convention on block A. I'll have rightward positive. And then for the Y, it doesn't matter if I say up or down here. I'll say upward positive. Doesn't matter there. We don't have any acceleration in the Y-axis. All right, moving on to block B. So now when I look at block B, I'm looking at my rotated coordinate system. You can draw a separate diagram if you're still needing help with that. That's worth spending time on, but we've been working on this for a little bit here. So what's in contact with block B? Well, I've got the cord in contact in two directions. To the right, I have the cord between B and C, so I'm calling that T double prime. And to the left, I have the cord between A and B, and I'm calling that T prime. So you can see some third law pairs showing up here. Hopefully you're seeing those, right, in the tensions. Okay, very good. And what else is in contact with block B? Well, it's in contact with the surface beneath it. That surface beneath it is going to exert a normal force perpendicular to that surface. So that will be what I'm going to call N sub B. That's this right here, right? That direction there. And the surface beneath it also exerts a frictional force, kinetic frictional force. Remember, block B is sliding up the incline. So I'm going to add that over, pointing to the left. So that leftward arrow is actually a combination of frictional force and tension to the left. And now, of course, we have to put our one invisible force, which is the weight, and that will end up in this quadrant here. The weight of block B, that is our one off-axis force. It's our one off-axis force. I'll say positive um, to the right, and then or positive upward along the incline, and then positive upward perpendicular to the incline. Okay, so that's all our forces. I always go through and check to make sure that my stuff is complete, that I'm looking at all contact points, and that I consider for every surface contact, I'm considering frictional forces and normal forces. And then, of course, making sure that our notation's good to go. So now we're ready to render equations from these free body diagrams, which is a big part of our reason for creating them. So I'll do X first, then Y, as I usually do. So starting for free body diagram for A, I've got T prime positive x minus f sub a is equal to the mass of block A times its acceleration. Now this is an inelastic cord, so these bodies are going to be accelerating together. And I understand that for this very first part that we're told that block C descends with a constant velocity, but I'm going to actually bring that information in later. I'd rather do the more robust version of the problem where it's dynamic, meaning it is accelerating, rather than start with something simpler. So I'll set up for in general, and then you can apply it to anything. So I'll do free body diagram for B here, T double prime. This is a big one, minus frictional force minus the tension going to the left. And don't forget the component of the weight that's directed, that lies along the x-axis here. So that's going to be um, the weight of block B times sine of phi. And that's equal to mass of block B times its acceleration. Again, I'm using the same symbol for acceleration because all these bodies move together. That's my x-axis statement, second law statement for block B. And block C doesn't really have an x-axis statement. It only has one statement, right? Because we only have any forces, both the forces that exist are along the same axis. So I can write this one really simply. Weight of C minus that tension is equal to the mass of C times the same acceleration, because again, they're going to move together. However, block C moves downward, right? That'll be the same speed at which the other blocks are moving along on their particular axes. Okay, so that's our X statement. Let's do our Y statements. We need those as well. So I'll do that for block A, normal force minus the weight of block A. And in this case, my acceleration in the y is going to be 0. So I can just go ahead and fill that in right here. I'll do block B, normal force B, minus the component of weight that points in the negative y, cosine phi, equal to 0. That's my y-axis statement. And then I don't have an additional statement for block C. So I've got basically 5 statements here that I've rendered. And I also know what I also know about these cases here. I'll change color, is that F sub A, let's sort this out, is going to be equal to coefficient that's given, mu sub K, times the normal force at that interface. And that normal force I'm calling N sub A. So kind of nice notation there, helps to keep things straight for me. The frictional force on block B, mu sub K, same coefficient. Same coefficient doesn't mean same force, right? Same coefficient doesn't mean same force, because the force is a product of the coefficient and the normal force. The normal forces on blocks A and B are not the same here. Even if their masses were the same, they wouldn't be the same because block B is on an incline. So multiplied by the normal force on B. So I'm analyzing only one interface at a time. Okay, so these are the equations that you would have to work with, those 5 equations rendered from second law, and then you'd want to substitute in these expressions for your frictional forces, and that would allow you to solve for basically whatever you wanted to solve for here. For this first part A here, we're still assuming that block C descends with constant velocity. So for part A, what we can say is that acceleration is equal to 0. And that simplifies the equations that we just rendered, right? For part B, oh, that's just a different unknown. We're solving for mass of block C. And then part C asks us what happens if we cut the cord between blocks A and B. And when you get to that part, what I would encourage you to do is look at your free body diagrams and see, like, what do my free body diagrams look like now after you've cut that cord for that part, and do a redraw there. Block A will be out of the situation, of course, but blocks B and C will still be in motion, and then they'll be accelerating in that case. Okay, all the details are in the written solutions, but hopefully this gets you off to a good start.